All right. So, yeah. All right. So, good evening, everyone. I am Avik. I am a PhD research scholar at the Department of Electrical Engineering at IIT Madras. And today we are in the fifth week of our live session for Introduction to Wireless and Cellular Communications. So, if you recall the lectures of week 5, so in week 5, we continued with the discussion on the coherent and differential modulation and detection schemes, and we mainly thoroughly analyzed the bit error rate performance in fading channels. And if you recall, a table was shown which summarized all the BER performance in different scenarios for different modulation schemes, and then we also introduced the rice PDF for the rice distribution or Ricean distribution or Ricean distribution, whichever way you pronounce it, and also briefly introduced the Nakagami M distribution, and we looked into the aspects of interleaver, how interleaver is employed and why is it employed, so on. So keeping all these concepts in our mind, let's get started with our today's session. Okay, so I hope question number 1 and 2 is visible. So let's start with the first question. Okay, let me. Okay, so please read the first question. So DBPSK modulation scheme is used here. DBPSK stands for differential binary phase shift keying. So the rule is that the transmitter sends 0, okay, at the beginning of the transmission. That's the assumption. And the rule is that bit 0 is transmitted with 0-degree phase, and bit 1 is transmitted with 180-degree phase. First of all, it's binary, therefore only two bits are there, 0 and 1. So for bit 0, there's 0-degree phase. For bit 1, there is 180-degree or pi phase. Now, in the given question, if this binary bit stream 0, 1, 1, 1, 0, 0, if this bit stream has to be conveyed to the receiver, then which is the correct bit stream that has to be sent to the transmitter after doing the differential modulation that has been asked. Okay, so it's kind of like your data to be conveyed to receiver, that's known to you, that's given to you. Now you do this differential modulation scheme, and then you get some modified bit stream, okay, and that has to be actually sent to your transmitter for transmission. So this here actually is what you need to find. So this is like the correct bit stream to be transmitted. Okay, so this is at this point. That's what you need to find. That's the question. Okay, and this is given to be, I think, 0 1 1 1 0 0, like this. Okay, so as I was saying, we have to remember that in your differential modulation, or in your DBPSK scheme, the information is basically encoded in the differential phase. That's why it's known as differential binary phase shift key. So that is the idea. And here, if your bit is 0 and if your bit is 1, so the encoding is like, for bit 0 you'll have no phase change, 0-degree phase, and for bit 1 you'll have pi, which is 180-degree phase change. Okay, and for the transmitter, it is assumed, if you go back to the question also, it is mentioned that the transmitter sends 0 at the beginning of the transmission. So the starting bit that the transmitter is going to send is bit 0. So I'll write that up as well. So transmitter sends 0 at the start. Good. So now there's a simple rule actually. I mean, simple way you can solve it in just a very less time. But what's going on actually? I'll try to demonstrate that. So let's first draw the given bit stream that is given in the question, that the data to be conveyed to the receiver. So that is I think 0 1 1 1 0 0. Okay, yeah, 0 1 1 1 0 0. So that is 0. Okay, I'll just from here maybe 0 1 1 1 0 and 0. That has to be conveyed. Okay, now and we just know the rule here. For bit 0 0-degree phase, for 1 bit 1 180-degree phase. So I'll just write it here. So this is 0-degree phase change, and 1 means 180-degree phase change. Again another one, 180-degree phase change. So when I say phase change, so when it's 0, it's 0-degree, no phase change. When I encounter a 1, I change my phase. So my phase becomes 180-degree from 0-degree. Then I encounter another one, my phase becomes 360-degree from 180-degree, and so on, 540-degree, like that. Okay, so and this is again 0. I think someone wants to join. Okay, fine. So now this is the data to be conveyed. Now, okay, people are joining now. And now I will draw your DBPSK modulated wave, okay, from this given bit stream. So we know that, okay, let me initially, first of all, let's just demarcate these, bits. Let's say, so I think, yeah, I'll draw some lines. Whenever there is an incoming bit, I want to, track that using some vertical lines. So yeah, it's not very good, but okay. Okay, so yeah, in the DBPSK modulated wave, basically I'll start with a wave. Let's say we have this wave, you know so zero, I encounter a zero. So the rule is 0 degree phase change. My phase won't change, okay, it will remain the same, and so on. Now I encounter a 1. So what happens? 180-degree phase change. So it becomes like this. From here, there is a transition like this. Okay, there is a phase change like this. 180-degree phase change. Then it goes all the way till here, and again another one I encounter. So again, I'll have a phase change of pi, and similarly once again. Okay, I think I used the wrong color, but yeah, so I'm denoting the phase change transition by the red color. Now I encounter 0, so no phase change. And again 0, so no phase change. Fine. So it's not drawn to scale, but I hope you get the idea. So this is okay. This till now it's fine. Now I want to get the correct bit stream actually that has to be transmitted. So I would say correct bit stream to be transmitted. Okay, so transmitter sends 0 at the beginning of transition, that is our assumption. So in the starting I will have 0, so let's say 0. Okay, and just extend these dots. Okay, fine. So initially I have 0. Now for the bit 0 there is no phase change, right? I see no phase change, so it remains 0 after this first bit. Now after this 1 arrives, I have a phase change of pi. So a phase change of pi will mean a transition from 0 to 1 or 1 to 0. That's the idea. So from 0, due to this phase change, I will jump to 1. There are only two levels, it's binary. Okay, someone wants to join again. Okay. So there will be this transition. And this is what? This is 1. Okay. Similarly, again, at this point, I encounter another phase change of pi. So I'll get another transition from 1 to 0. Again, here I'll have another transition from 0 to 1 due to this phase change. Then there is no phase change. Okay. So this remains at 1. Again, there is no phase change. So it remains at 1. Okay. So this is your actually this is your actually transmitted sequence. The stream that I have drawn on the bottom. So this picture is clear, right? Okay. Okay. So your actual transmitted sequence is basically that's what you get. What's that? 0 0 1 0 1 1 1, which I have drawn on the lowermost side. Okay, so this is what you need. This is your answer basically. This is sent to your transmitter for transmission. Now, okay, all this we have looked graphically. I hope there is no complicacy here, but if you want to do it very quickly, so essentially you see what's happening here. By now, if you have already observed, it's okay. So you see, this is the starting bit. Okay, this 0 is the initial starting bit of transmission. You take this bit, okay, you take this bit and you take this starting bit that has to be sent, that has to be conveyed to the receiver from here, this one, and you do this modulo 2 arithmetic, which is your XOR basically. So I'll write it XOR. Okay, so you are familiar with, I think, from digital electronics or some course, you should be familiar with the idea of an XOR operation, which is an exclusive OR operation. So what happens is that whenever the two bits are equal, the output will be 0, and whenever they are not matching, they are unequal, let's say 0 1 or 1 0, the output will be 1. So this XOR is actually going here. Okay, similarly you take this and take this to the XOR that is coming here. Okay, and so on, it repeats. This one and this one, you XOR, you get it here. So this, you get it here. You get it here. Yeah. Okay. Fine. So this is what's actually happening. Now So it's essentially XORing. Okay, so if now I denote this the data that I want to convey, which was given in the question to be, let's say, some IK bit stream, and this data that is actually transmitted to be some BK, let's say, sequence, then what's essentially happening is, so you can visualize it like this. So okay, I'll switch back to my blue color. So I have this, incoming bit stream, and I have this XOR. Okay, XOR. Uh, this gives my actual transmitted sequence, but I'll have, sorry, I introduce a delay. So this is BK minus 1. Okay, so yeah, and so basically the equation that you get is BK equals BK minus 1 XOR with IK. Okay, that's the rule. So BK is your actual transmitted sequence, and IK is the given bit stream that you want to convey to the receiver. Okay, so this is the idea, and since we mentioned in the problem that transmitter sends 0 at the beginning of transmission, so the assumption is that B0 is 0. Okay, that's the assumption. So now you can you already have this IK, right? You have this IK that was given to the question, given in the question. That was the data that you wanted to convey. So that was this 0 1 1 1 0 0. So 0 1 1 1 0 0. So this is basically your I1 comma I2 comma I3 comma I4 comma I5 and I6. Okay, so your I1 is 0, I2 is 1, I3 is 1, I4 is also 1, I5 is 0, and I6 is also 0. Now you calculate the BIs. So if you put k equals to 1 in this equation, so you get B1 equals to B0 XOR I1, which is B0 is 0 by our assumption, and I1 is 0. So 0 XOR 0, you get 0. Similarly, B2 you find, which will be B1 XOR I2. So you'll get B1 you calculated to be 0, XOR with I2 is 1. So you get 1. Now similarly B3, it's a recursive process, right? So you get 1 XOR 1, which is 0. Finally, this one will be, yeah, I hope I didn't make any mistake. Anyways, you get the idea, right? So your BK basically, which is your B0, B1, B2, B3, B4, B5, B6, that is this sequence, right? This sequence. This is 0. I mean, it starts with like 0 here. So this is B0 is 0, and then P1 is 0, P2 is 1, then 0, then 1, 1, 1, like this. Okay. So this is your answer. This is your actual bit stream that is to be, that is transmitted actually. Fine. So now if you go back to the options, I think it's option A. So your answer is option A. Okay. So that's the simple rule. Only this is the main idea. This box. Okay. All this graphs and all, they are just for understanding. So yeah.
Sir, you can tell you have clarified all the way.
Mm-hmm.
It is correct. But one thing I want to know that I want to know why we have applied XR here. Why we have applied XR due to the phase change or sequence of phase change or another logic is there.
Okay. I mean,
Yes, you have applied here XOR, which is
mm-hmm.
correct.
Yes.
So from what logic you have applied this only for XOR? Why not X and or other operation is there?
So if you try for any other, let's say OR gate, will OR gate satisfy
Hmm.
this requirement?
Oh yeah.
I mean, in this case, no OR gates. See, because if I take this one and this one, if I apply an OR gate here, so OR1 will give me one, right?
One.
So this
One.
will be incorrect. This is not satisfying this requirement. So XOR is the
Okay.
only gate that will satisfy this.
Only option is there. Okay.
Yes. That's the rule actually. This circuit. This is how
Okay.
you get
Okay.
it. Okay. So
Okay.
this
That is the
XOR.
logic actually.
Yeah. So and modulo 2 is like
Yeah.
basically XOR. So whenever we deal with this binary fields, like XOR gets extensively used, and they are used in like shift registers also, like for these purposes. So yeah. So
We are
yeah,
using
XOR.
shift
XOR.
register actually.
Yes.
Yeah.
XOR. Okay, you can
Okay. Okay.
look it up in more details, but yeah, that's the idea. Other gate won't work actually. Yeah,
Okay.
fine, good. So yeah, let's now move to the second question. Okay, read the second question. Uh, and by the way, I mean, people can simply address me by my name, or you can just call me Avik, because I think in the audience there are many people who are actually senior to me. So yeah, I would prefer everyone calling me simply Avik. Okay. Anyways, so yeah. In the second question, okay. So we have a coherent QPSK modulation and detection scheme. The symbol duration is given to be 10 microseconds. Okay. So although it doesn't look like a micro, it's more looking like a U, but assume it's micro. So 10 microseconds is the symbol duration. Coherence time of the channel is 5 milliseconds. 50 symbols are being used for the purpose of channel estimation. Then we are asked to find the data rate. Okay, that's the setup, and we just need to go back to our lecture notes for this. Okay, so you remember. Okay, So this diagram, if you remember, okay, another comes like this, again it continues. Okay, sorry. In coherent detection, we saw this diagram, right? So this was your TC, coherence time, and that's 5 milliseconds. It's given to be 5 milliseconds. This shaded region is where you do the channel estimation. Okay, and it is mentioned that okay, 50 symbols are being used for purpose of channel estimation. So 50 symbols. Okay, and this is the portion where you actually do the data transmission, and you will have the data rate and the throughput, and these shaded regions are reserved for channel estimation. Again, you do channel estimation here. Okay, after an interval of coherence time, you estimate the channel. Okay, in coherent detection. Fine. So channel estimation, right? So this was the diagram. Okay, we have to remember this. Now it is given that the symbol duration is 10 microseconds. Okay, so symbol duration which is denoted by TS is 10 microseconds. Okay, coherence time I have already written. So the channel has to be estimated after every coherence time. Now, okay, one symbol means like 10 microseconds, right? That's the symbol duration. So 50 symbols means 500 microseconds, or in other words, 0.5 milliseconds. So this much actually, this much is your 0.5 milliseconds. Okay, so this remaining, this duration is 4.5 milliseconds. Okay, fine, good. So the observation is that in every 5 milliseconds, which is your coherence time, 0.5 milliseconds is dedicated for channel estimation purpose. Okay, now we have all the tools basically. So you have to find okay, first of all, okay, what's the modulation scheme? QPSK. So QPSK. So for QPSK, you have to remember one symbol means, because we need to find the data rate, and data rate is in BPS, or the bits per second, right? Bits per second, kilobits per second, depending on the magnitude. So you have to find the data rate in bits per second. Now in QPSK, how many bits are there in one symbol? Can someone just quickly answer me?
2
2 bits.
bits.
Yes, 2 bits. Basically 00011011. Okay, these are the symbols. So yeah, so when you find the symbol rate and then you multiply with the number of bits per symbol, you get the bit rate or the data rate, right? And for that, so your symbols per second, that's or in other words your symbol rate uh, times bits per symbol. So how many bits are there in each symbol, which you know is 2 for QPSK. We just mentioned it. So if you do this, so basically you are left out with bits per second. But now that's not the end. Effective data rate would actually be derived from this diagram. So I don't have my entire coherence time, right? I don't have my entire 5 milliseconds for transmission. 0.5 milliseconds is already reserved. So I have to utilize the remaining 4.5 milliseconds for data transmission. So you have to multiply with that factor, okay? That factor of transmission. So that will be like, you can say, useful data time, okay? That basically governs your throughput divided by the total time, okay, which is 5 milliseconds. So the useful time is actually the 4.5 milliseconds. So this fraction you need to consider, okay? This will actually give you your data rate, okay, and data rate in bits per second. Fine. Now so let's do that. So this is the useful data time. It's like 4.5 milliseconds divided by total time is 5 milliseconds. So that's the fraction. Symbol rate. What is symbol rate? Symbol rate is simply the reciprocal of your symbol duration, right? Which is 1 by TS, correct? How many symbols are there in 1 second? Which is simply the reciprocal of their symbol duration, right? And times, we just saw that this is 2. So 4.9 by 5 is 0.9 times 1 by TS is 10 microseconds. So 10 into 10 to the power minus 6 seconds times 2. So this is 1.8 into 10 to the power 5 bits per second, which is 180 kilobits per second. Okay, that's your data rate. So option A. Option A is the answer. Okay, simple. Yeah, straightforward. So let's go to the next one. Okay, let's look at the third question. These are very simple questions. Just we need to apply the formula. So we saw a lot of expressions for the bit error rate in the week 5 for different modulation schemes, different scenarios, whether we have only AWGN, whether we have fading also, like that. So in the third question, your gamma B, that's your SNR, EB by N naught. Okay, I think okay, I think there is actually there's a typo actually in third question. Actually, this gamma B value is not mentioned. So what's there is actually, think, wait. Okay, so this gamma B, your EB by N naught, is actually given to be 7 dB. Okay, so there's my apologies for this. So it's actually 7 dB. It's not printed here, okay, in the question. So of course you need that information, otherwise how will you find the bit error rate? And we have QPSK modulation scheme. We have to find the bit error rate. So your bit error rate for QPSK, and this is simply in AWGN. There is no fading, otherwise it will be mentioned, right? So this is given by the Q function, and we need to use the exact expression, okay, for the bit error rate. So the exact form is Q function of square root of twice gamma, okay. And now but before that we need to do one small thing, which is converting from dB to linear scale. So your 10 log base 10 of x is 7 dB. So your x, you will find 10 to the power 0.7, which is approximately 5.0119, something like that, okay. To verify it, and if you just put it here, so that's q of square root of twice 5.0119, and this is approximately q of 3.1666 and so on. That is approximately 7.7 into 10 to the power minus 4, okay. So this not printed in question, okay. I'll just add this remark.
Sir, how that Q value calculated? Please show me.
Okay, so okay, this actually you can this wait this value you just refer to your online Q function, sorry, calculator, okay. You have
Yes, sir, that can be done through online.
or Q
Yes,
table.
sir, that can be done through online, but I don't know how to proceed.
Oh, okay. So I mean, so you or you some Q tables are also available. Okay, you can refer to that also, or so you just simply okay, let me just show you a demo. So Q function calculator I searched. So Wolfram Alpha is the first website that comes. Okay, so I'll just open that. It's a bit slow. Okay, so you see this window here, the Q function calculator clearly mentioned. This is the argument x. So x is the parameter that you need to pass. Okay, so in our case, if you see Q of 3.166, right? So 3.166 is your x, is the parameter that you need to pass. So if you enter 3.166, okay, so I'll restrict to 3 decimal places, and you have to click this submit. Now it calculates, and you see it shows this error function form. Actually, see, you have this form, right? This relation between error function and your Q function. So yeah, you see the result. The result is displayed here, 0.00077, which is, in other words, 7.7 into 10 to the power minus 4. I just wrote it in that form, right? So simply just do a Google search to open this Q function calculator, and you can just do it.
Sir, in exams, how can we done, sir?
Okay, in exam, if your Q function is not, I mean, if you need Q function value, then it will be mentioned in the questions. Like in previous weeks, we have seen, right, for calculating outage probability, and so Q of some value is mentioned. Okay, you don't need to worry, or else you will be supplied with that value. That you know need not worry actually. Okay, so sufficient information will be present. Okay, this is just, I mean, for
Okay,
just,
sir. Thank you.
yeah, don't worry. And also, in the worst case, let's say assuming the worst case, if you don't have anything, don't have access to anything, then what you can do is you can do the upper bound approximation for the Q function. That fairly approximates your true value or the exact value of the bit error rate. So in last week, if you remember, we started with one problem, upper bounding our Q function and approximating it. So we will solve another problem for that also. So you have a exact expression, upper bound approximation expression for the Q function. In case your Q values are not available with you, you can simply apply that formula and you find the calculate the value. So I'll show that next. Okay, so third question is done. Now fourth question is an extension of the third question. We have to find the symbol error rate using exact expression, and we know that one QPSK symbol consists of 2 BPSK bits. That's fine, and we need to use this idea and the concepts of basic probability to calculate the symbol error rate. Okay, what's the symbol error rate? So can anyone tell me what's the symbol error rate? How do we actually find the symbol error rate? So if I denote this by, let's say, some PB, let's say, that's the bit error rate. Now we need to find the symbol. So this is continuation of question 3. Symbol error rate, which is your PS. Let me denote it by PS. That's what we need to find. Yeah, how do we do this? We already found the PB, and we know that.
Excuse me, sir.
Yes.
Sir, in earlier problem, we were given with the value of EB by N naught
Hmm.
7 dB. So
Hmm.
why we converted it in means we have converted this value 7.
Hmm.
Uh, so
Yeah,
why we have converted, sir?
that's the rule, because this is in the linear scale. This Q function value, this bit error rate that you specify for QPSK, BPSK, all these modulation schemes, this argument, this parameter of the Q function is in the linear scale. That's why we are moving from the dB or the log scale. The value is given in the log scale, which is 7 dB. So we have to first convert it to the linear scale and then apply to this formula.
Apply to Q function.
Yes, and
Okay.
this is opposite to the case of log normal shadowing. In, if you remember previous weeks, in log normal shadowing, basically that's log, that's Gaussian distribution in the log scale. That's why your parameters like beta, sigma, you remember that Q of beta by sigma, there the values of beta and sigma will be in dB scale. So until and unless you are given a log normal shadowing environment, um, you have to always convert to linear scale and apply to this formula. So yeah, in
Okay. So
general,
if
yeah.
log normal shadowing environment is given,
Hmm.
then we will take Q function in dB.
Yeah, so you remember that formula of probability of outage, which was given by Q function of beta by sigma. So there your sigma, which was the standard deviation of your log normal distribution, that's in dB because it's log normal. It's normal in the log scale. So therefore, all these parameters are in dB. So that was an exceptional case. So otherwise,
Uh,
in general, in these cases, you always convert from dB to linear, and then only this you apply to this formula. Okay.
okay, okay.
Yes.
Otherwise, we will have to take it in linear.
Yes. 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 So this
Okay,
is
linear
your
scale.
this 5
Okay.
point, okay, where is that? Okay, this is in linear scale. Yeah, fine. Yeah, so now, yeah, for the symbol error rate, how do I do it? If PB is the bit rate, and I know that one QPSK symbol is 2 bits, right? Contains 2 bits. So what is my symbol error rate? Can anyone give me some idea how to proceed about this? I already have my PB, bit error rate. I already have. I already calculated in the previous question. What will be my symbol error rate? How do I now get my symbol error rate? Any thoughts? Okay, so what are the symbols? What are the possible symbols? 0 0, 0 1, 1 0, 1 1. You remember the constellation, right? So each symbol has 2 bits. Now my symbol error rate. So when does error happen? When there is at least one bit flip. Out of the 2 bits, at least one of the bits it's corrupted, is flipped. Basically error means 0 to 1 flip or 1 to 0 flip, like that. So your PAs is like at least, it means at least one bit is incorrectly received at the receiver. So that is that, or in other words, what can I say, which is the complement of, which is 1 minus the probability that both bits are correct, right? Correct. You agree with this or not? I have my ideal situation where both the bits are correctly, transmitted, there is no error. And if that doesn't happen, all the complementary cases, so at least one error or both errors, that will be basically, that will govern my symbol error rate, right? PS. So that's why I wrote 1 minus this probability. Fine. Ask me if you have any queries with this. Okay, so great. If not, then it's fine. Okay, so I'll go to the next page. So I'll write it once again. So this is 1 minus probability that both bits are correct. Now, what is this probability? What is this probability that both bits are correct? Given that your bit error rate is PB. Yeah. So let's say I transmit 0 0, I get 0 0. With what probability? And these are all independent symbols, right? There is this independence you can always assume. So are people there? Yeah, is my question clear to you? Like I'm asking, what's the probability that there is perfect transmission? There is no error. There is no error in any of the bits. Both the bits are correctly transmitted. Let's say 0 0 is transmitted, 0 0 is received. So what is that probability with which this happens? Probability that both bits are correct. if probability of 1 bit error is PB, then with what probability does this happen? Okay, I'm not sure. Okay, first of all, am I audible to everyone? Just can anyone confirm?
Yes, sir.
Yes,
Okay,
sir.
okay, 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 good, good, good. So yeah, so this is basically your 1 minus C for the first bit there is no error. This is error. This is bit error. So probability of no bit error would be 1 minus PB, just the complement, no bit error, and there are 2 bits and they are independent. So for the first bit I will have this term. Similarly for the second bit I will also have correct reception, which is 1 minus PB, which is no error. No error. This is no error for first bit. This is no error for second bit. Correct. This is simple. So what is this effectively? 1 minus PB the whole squared. So if you expand this, what do you get? 2PB minus PB squared. Correct? Fine, it's very basic probability. So and note that it's not equal to 2PB. Some people might think, okay, for QPSK one symbol has 2 bits. Okay, if I have the bit error probability as PB, then simply I can say, okay, straight away conclude that symbol error probability would be twice of that, twice of PB. But that's not exactly the case here. It's actually 2PB minus PB squared. And so what's essentially happening here? Let's say you okay, so this is what actually if I calculate this value, PB I already calculated in the previous question to be this 7.7 into 10 to the power minus 4. So if you just plug in those values minus this squared, you will get approximately 1.55 into 10 to the power minus 3. Okay, and that's your option A. So option A. And what's actually, I mean, what does it mean when you have symbol error? So you see, say your 00 symbol is transmitted. Okay, then what's the symbol error rate? It's like these cases. So you have I mean the error cases would be you transmit 00 but you actually receive something else, which are like 0 1 1 0 or 1 1, the other cases, remaining 3 cases. So it's like this. So this means the first term means 0 1 is received given that 0 0 is transmitted. Similarly, the second terms means 1 0 is received given 0 0 is transmitted, and so on like this. Correct? And in fact, this is just I chose for, I mean, if 0 0 is transmitted. Similarly, you can do it in generally. Uh, if you transmit this, so what are the errors? These. Correct? Another case could be you transmit 0 1. So what are the error cases? 0 1 goes to 0 0, 0 1 goes to 1 0, 0 1 goes to 1 1. Correct. Third case could be you transmit 1 0. The cases of error could be 1 0 goes to 0 0, 1 0 goes to 0 1, and 1 0 goes to 1 1. And finally the last case is you transmit 1 1, 1 1 goes to 0 0, 1 1 goes to 0 1, and 1 1 goes to 1 0. Fine. These terms, these are the errors, right? So these values are my, which I just calculated here, 2 pb minus pb square. Basically this is 2 pb minus pb square. Again this is 2 pb minus pb square. See, at least one error is there. From 0 0, if I jump to 0 1, one bit is flipped. From 0 0, if I jump to 1 0, one bit is flipped. From 0 0, if I jump to 1 1, both bits are flipped. So at least one error is there. That's why 1 minus no error is there. So again this one, 2 pb minus pb squared. Again this is 2 pb minus pb squared, and the assumption is that your transmission of 0 0, probability of transmission of 0 0 equals probability of transmission of 1 0, 0 1, and 1 1. They are all equally likely with equal probability 1/4 they are transmitted. Okay, so all these, this is 1/4, this is 1/4, this is 1/4, this is 1/4. So therefore if you substitute these, so you simply get 2 pb minus pb squared, right? So this is actually, I mean, mathematically, and in a compact form, how can you write this? So ps is basically some probability of ith symbol is transmitted times it goes to some jth symbol, okay, which is not equals to I. So ij belongs to these symbols 0 0, 0 1, 1 0, 1 1, but it goes to a jth symbol which is not the same. That's why error is happening, such that j is not equals to I. So that's kind of a compact expression for your QPSK. This is your symbol error rate. Fine. Easy, right? Simple probability. Okay, so we're done with the fourth question. Now the fifth one. Yeah, okay, someone. Okay, now in the fifth one we need to find the bit error rate for QPSK. SNR is given to be 9.5 dB. Now you have to use the upper bound approximation for QZ. So as someone was asking during the third question that, okay, what if I don't have access to Q value? Let's say I don't have internet, I can't search Google, I don't have been mentioned about any Q value in the question, anything. In the worst case, you can use this upper bound approximation, which is a good approximation. So okay, let me start from here itself. So this is your SNR is given, which is also your EB by N naught, is 9.5 dB, and once again I'll just convert it to linear scale. X you're getting to be 8.9125, like that. So you need to use upper bound approximation. That's mentioned in the question, and I derived in the last week, the first question of last week. So that is given by, or it is discussed in the lecture notes as well. You refer to the lectures, that the upper bound approximation was this, e power minus this. Yes. So in the last week's session I derived this as well. So yeah, this is your approximation. You need to use this formula, 1 by square root 2 pi e power minus z square by 2 by 2. You put your value of, say, whatever z, whatever is your parameter. In this case it's 8.9125, the SNR, and you get the value. Okay, so your
Sir, what it is? E raised to the power?
e raised to the power minus z square by 2, whatever is your argument for
Minus
the
z
q
square by.
function. I am
Okay.
writing here q of z, so for that it will be e power minus z square by 2, whatever is the parameter inside the bracket.
Okay, sir.
So bit error rate for QPSK, okay, no, sorry, what I am writing, wait. So your approximate bit error rate. So yeah, I mean you can write AWGN because there is no fading. This is approximate, that is your 1 by, this is approximately e power minus z square. What was z square? Okay, just a minute. Yeah, so okay, okay. So yeah, so bit error rate for QPSK in AWGN. So the setting is this, right? It's QPSK and it's AWGN because there is no fading. It's not mentioned. This is given by, sorry, Q of square root twice your SNR, your gamma, correct? And now I just wrote the approximation before. What was the approximation of the Q function? This 1 by square root 2 pi e power minus z square by 2 whole divided by 2, right? So this is my z, the whole thing sitting here, square root 2 gamma is my z. So you use that, use the approximation. This is minus z square by 2, so this comes out to be minus gamma by this. Okay, someone I think wrote in the chat box. to solve each problem it takes. Does it really take 20 minutes? I mean, if you are asked to find a bit error rate, you can simply plug in the values and just find the value. So here I am taking time to ensure that everyone understands it. I'm not rushing. I'm explaining everything slowly. That's why it's taking time. But for you, I mean, all the formulas are available. So you just plug in and get it. I understand some problems may take a bit longer and you have to carefully calculate. So yeah, I can only say about INSEM, I mean the final exam, that the pattern will be similar to the assignments. Now exactly how many questions will be there, that's I'm not sure about that, but yeah, you will be informed about those things in due course. So yeah, but the pattern will be similar to your assignments questions only. Yeah.
Okay, sir. Thank you.
Yeah. So yeah, so this is the upper bound approximation I used. Everyone sees it? Sorry. So you substitute the values. Gamma from 9.5 dB, we saw that it appears to be this in linear scale. So this is, if you substitute the values, e power minus 8, this thing. So you get nearly 1.27 into 10 to the power minus 5. That's your answer. Okay. This is your option B. Fifth question, option B. Option B. Fine. So this was the case that you are asking. If you don't have any value of the Q function, you can use this approximate formula using the upper bound approximation. Fine. Yeah. And I think as a quick exercise, you can
Sir, means what we have done, upper bound approximation means?
upper bound
What?
approximation means upper bound approximation. That's the upper bound approximation for Q of Z. The Q function is upper bounded by this quantity, e power minus z square by 2 by z.
Okay.
Just in the
Okay, so
previous,
this is upper bound.
yeah,
Ha.
obviously. So this is what I wrote here. Okay.
Okay.
So yeah.
Mm,
So this is z. This is z. Yeah. This is the upper bound. This is the upper bound approximation. I derived this in the previous week also. You can refer to my previous video also, and or you can refer to the lecture notes also. But I have derived it also. Derivation was not done in the lectures, but I have derived in my previous week's session. You can refer to that recording. So yeah, that's the upper bound, and that is fairly equal to your exact value. So if you actually calculate the exact value from the Q function calculator, instead of using this approximation, you would be getting something around 1.21 into 10 to the power minus 5, which is fairly close to this, approximate value, which is 1.27 into 10 to the power minus 5. So yeah. So that's it. Now going to the sixth question. Okay. Sixth question. Yeah, again a similar question for differential BPSK. What's the bit error rate if SNR is 5.4 dB? Okay, and again assume only AWGN with no fading. Differential BPSK, again all you have to remember is that table that was summarized by Professor David for different modulation schemes, what performance you have under different settings. So this is your bit error rate for differential BPSK in AWGN without any fading. That, if you recall your lectures, the expression was given by half e power minus gamma. Okay, and gamma is your SNR, which is given in the question to be 5.4 dB. Again, if you convert it to the linear scale. I'm writing this again and again, but by now it should be, simple to you. So this is approximately 3.4674. So this in linear scale is 3.4674. You put that value here, and you get half e power minus 3.4674, which is approximately 0.015. 0.015 is our option D. So our answer is option D. See how much time did it take? So that whichever problems are simple, straightforward, formula based, it will take hardly a minute to solve. So you'll have calculators and you can easily solve it. So, and question number 7 also, it's similar again. You have the closed form expression for all this and just substitute the values, that's it. This time in question number 7 you have coherent BFSK. Coherent BFSK was also, the value was also, the form for the bit error rate was also summarized in that table. SNR is 15 dB, and this is assuming Rayleigh fading environment. Okay, this is not just AWGN, this is Rayleigh fading is there. So again, go back to your, lectures, recall lecture table for bit error rate. That from that table you can find that the bit error rate for, I need coherent BFSK in not AWGN but in Rayleigh fitting, that was given by this formula, half 1 minus square root of gamma, this is capital gamma, square root of capital gamma by 2 plus gamma, where your gamma is average SNR. Remember, your small gamma is your instantaneous SNR, and this average gamma, this average SNR, which was a capital gamma, is basically the average. So it's the expectation, right? Expected value of small gamma. This was the relation. Everything was discussed in the lectures. Just go back in case you find any difficulty. So this gamma is actually given. So you see in the question, the average SNR is given. Average SNR is 15 dB. So this gamma is given to be 15 dB. And once again, the first step, which is converting from dB to linear, you get x to be 31.622776. Okay. Yeah. So you just this is 31.62277. So you substitute that value here. Okay. Divided by 33, because it's 2 plus gamma. So if you solve this, you'll again get approximately 0.015. So for the 7th question, 0.015, option C. Option C is the right answer. See, once you know the formula, it's just 1 minute. Okay. So these are straight way, formula based, you can solve it easily. Okay, so far so good. Now read the 8th question. Or if you have any doubts till now, please ask me now.
Sir, what is the answer?
Answer is 0.015, which is
0.015.
Yeah, that's not important. You can just calculate it in your time. The formula you have to remember, you just have to carefully calculate it. So it's 0.015, which is option C. Okay, good. So Now read the 8th question. Okay. Read the 8th question. So GMSK system is given with SNR of 10 dB. Now it says what should be the SNR in dB of a BPSK system such that the bit error rate remains the same for the same BER performance, okay, as that of the GMSK system. My bit error rate is same for GMSK and BPSK. If that's the case, then what should be the SNR of the BPSK system? That's what's being asked. So GMSK, if you remember, it was that Gaussian minimum shift keying, and it was discussed in the last lecture of week 5. So you remember that graph, BPSK has the superior performance, slightly better performance as compared to GMSK. That if you remember that margin of that SNR, it was exactly 1.55 dB. So it was mentioned, it was derived in the class. So GMSK has a slightly worse performance than BPSK. Okay, let's see how we do it. So okay, so question 8, GMSK system. The SNR of the GMSK system is given to be 10 dB. Okay, let me denote it by gamma GMSK. Now we are asked for the same bit error rate performance, what should be my SNR for the BPSK system? So this, let me denote it by some gamma BPSK, is what we need to find, and constraint is same BER. Okay, same BER constraint, that's the given constraint. And in case you are wondering what this GMSK is, this is Gaussian minimum shift key. Okay, this is GMSK full form. Okay, so you remember that the probability of error for your GMSK. So Professor David mentioned that that parameter which was the bandwidth and time product, okay, BT for GMSK, if that's 0.3 or something like that, so you get this probability of error for GMSK to be approximately Q of the Q function of square root of 1.4 times gamma. So gamma I denoted by the gamma SNR for the GMSK. Okay, so refer lectures. Okay, this was shown in the last lecture. And what about BPSK? BPSK I already know the expression, that is Q function of square root of 2 gamma, correct? Square root of 2 gamma BPSK. Okay, this is known. Now if I am told in the question that same bit error rate means for the two systems the probability of bit error are equal. Now if you equate these two Q functions, so what do you get? Basically 1.4 gamma GMSK equals to 2 gamma BPSK. Fine. So your gamma BPSK is how much? 0.7 times gamma GMSK. Okay. Now in question it is asked like, for GMSK system with an SNR of 10 dB, what should be the SNR of the BPSK system? So this gamma BPSK is what you need to find, and that too in the dB. Okay, SNR in dB. So this, so far we are in the linear scale. Now in order to find the value in dB, what should I do? Take log 10 log base 10 on both sides. So if I take 10 log base 10 on both sides, what do I get? 10 log base 10 of gamma BPSK equals 10 log base 10 of this whole term, say 0.7 times gamma GMSK, and whenever there is product inside logarithm, you can split it by addition, right? Log of xy is equals to log x plus log y. So I can write it like this. Correct? So this is what? This is your, sorry, this is your SNR of BPSK, gamma BPSK in dB. So let me denote it by this. And similarly, this term here is your gamma GMSK, the SNR for GMSK in dB. Okay. So what do you get? Gamma BPSK in dB equals this value. If you calculate 10 log base 10 of 0.7, you will get minus 1.55 dB, and plus this is gamma GMSK in dB. So and this is equal to minus 1.55 plus, what is your gamma GMSK in dB? What is the SNR of GMSK system? Already given in the question to be 10 dB. You just put that. This is 10. So this is, okay, sorry. So this is, it's not working. Okay. So this is 8.45 dB. Okay.
Sir, how it is 10 gamma GMSK in dB?
It's given in the question. Read the question.
Okay, sir.
So you have to follow, right? You have to be attentive. You have to follow. So, and I'm dictating all the steps also. So it's given in the question. GMSK, the SNR is 10 dB. It's given in the question. So you get 8.45 dB. So you see all this. This was directly mentioned that this value 1.55 is the margin between these two. So you see, for BPSK, I need an SNR of 8.45. For GMSK, I needed 10 dB. For BPSK, I need 1.55 less power, less signal to noise power, right? So therefore, BPSK has better, for the same bit error performance, BPSK has slightly better performance. Okay, so this 1.55 is all that you need to remember. But I just showed how this 1.55 margin is coming. Okay, just simply by calculation. So this is your answer, and if you check the options, it is option B, 8.54. Straightforward. Okay. Okay. Now we have ninth question. Okay, read the ninth question. It's based on interleaver concept. Read the ninth question. Okay, hopefully you have read the question. So it says that there are 12 code bits labeled as C0, C1 and so on up to C11. 12 bits are passed through a 3x4 interleaver, and the output, that of course interleaver is at the transmitter side, so the output of the interleaver is the transmitted bits, which are denoted by T0, T1 and so on up to T11. So the sequence will be different. You remember the concept of interleaver. They're used to randomize the errors. Whenever there is a burst error, it tries to mitigate that situation, avoid the situation by randomizing the errors so that your error correction is possible. So the transmitted bits are this T0, T1, so on up to T11, which are transmitted using BPSK modulation. Now the channel turns out to be bad momentarily, as a result of which these three transmitted bits, T4, T5 and T6 get corrupted. Let's say if they were some 0, they get changed to 1, let's say. So they are corrupted, and then you have to find what are the code bits that are obtained incorrectly at the receiver after de-interleaving. So you do interleaving at transmitter, and at the receiver also you have to do the reverse operation, which is de-interleaving. So whenever you encounter a interleaver, it is automatically implied that it is coupled with a de-interleaver at the receiver as well. Okay, so if these transmitted bits are corrupted, then what are the code bits actually which are incorrectly obtained? That's what we need to find. You are given the bits, the T bits, T4, T5, T6, that that have gone wrong. So what corresponding code bits, CI, what are the CIs that are corrupted corresponding to T4, T5 and T6? That's what you need to find. And you remember the structure, so you have to draw that structure. So okay, question number 9. So 12 code bits, okay, and I have a 3x4 interleaver at the transmitter. So of course 3x4, if you have a 3x4 matrix, how many elements will that matrix have? 3 times 4, right? For an m cross n matrix, it has m times n elements. So for a 3x4 interleaver, there will be 3 times 4, which is 12 bits. So you see 12 code bits are there, so it completely accommodates it. So okay, so these 12 code bits are in this sequence, C0, C1, C2 and so on till C11. Okay, now what my interleaver does is, so there will be a 3x4 matrix. Okay, like this. Okay, this is 3x4. So the data that arrives is in this sequence. It's in the proper sequence. So the data incoming data, that is in this sequence: C0, C1, C2, C3, C4, C5, C6, C7, C8, C9, C10, C11. Fine. And that data in is done column wise. Okay, how? See, this is the sequence: C0, C1, so on up till C1, C11. So you do it column wise. So first column, C0, C1, C2. Okay, we have reached the third row. The size is 3x4. Now you go to the next column. Then C3, C4, C5. Now you go to the other column, C6, C7, C8, and lastly C9, C10, C11. Okay, this is how your data is incoming. Okay, column wise happening. And for transmitting, for reading out the data, you do it row wise, along the row, horizontally. This is data out. Okay, so your transmitted data that is read out, that is transmitted, is row wise. Okay, first row, then second row, then third row, like this. Then what will be the sequence according to that if you travel along the row? So the first row, the elements would be C0, C3, C6, C9. Does everyone see that first row along the first row? Now I will come to the next row, which is C1, C2, sorry, C1, C4, C7, C10. Okay, and finally the last row, which is C2, C5, C8, and C11. Okay, row wise. Okay, I will mention here also. This was column wise. This was row wise. Okay, fine. Now this is what in my question, these transmitted bits are denoted by T0, T1, so on up to T11. So see the question, this T0, T1, T2, so on T11. These are the transmitted bits. So this is same as, these are same as my T0, T1 in that sequence, proper sequence, T3, T4, T5, T6, T7, T8, T9, T10, and finally T11. Okay, now it is mentioned that T4, T5, and T6 are corrupted during transmission. So I'll use the reading. T4, T5, and T6 have gone wrong. They are corrupted. So what are the corresponding code bits that gone wrong? So you see exactly the mapping. So this is C1, C4, and C7. These have gone wrong, right? So T4, T5, T6 corrupted implies C1, C4, C7 corrupted. So these are your corrupted code bits, C1, C4, C7. So look, the option is option C. The answer is option C, C1, C4, C7. So option C, C1, C4, C7. Okay, fine, is very simple. The concept was already discussed in the lectures. This was a simple case. Okay, so initially we had the dimension of the matrix for the interleaver 3 by 4. We arranged our bits accordingly in the interleaver, and then we found the transmitted data in that sequence. Yes, anyone wants to say something?
Sir, is it the arrangement done always? Means data in is arranged column wise and data out is arranged row wise?
Yes, until and unless it is, explicitly mentioned that I am doing it column wise. I mean, it is mentioned, then the default assumption is like this: data in is column wise, data out is row wise.
Okay, okay, sir.
Yes, and that was the idea. We have to, why this, data, if your data is read out in the reverse order, if your data in was in column wise order, and why the reason is your data out is in the row wise order is just to randomize the errors. So whenever we encounter a burst error, that will randomize it. Burst error means a chain of consecutive errors. So that is a difficult situation for the forward error correction schemes to work. Forward error correction schemes are meant for handling random errors, randomized errors in random locations. So in order to randomize my error locations, this change of sequence is followed, change of order is followed. Data in and data out are, kind of in opposite orders. That's why. That's the reason actually. Okay. And the default assumption is
Okay.
data in is column wise, data out is row wise. Okay.
Okay, so it is randomizing the sequence for
Yes. Not the
reducing the error.
sequence, not the, yeah, it is a sequence. Yeah, you say just to, randomize the errors. That's why.
Reduce the error.
No, not reduce the error. I mean, just to take care of the burst error. Burst error means consecutive errors, errors in consecutive bits. Let's say, I mean, 1, 2, 3, like
Okay.
that. So what the interleaver will do is it will randomize it to some different locations. Let's say 7, 12, 1, like that. Okay, that will be okay, easy for the
Uh-huh.
forward error correction scheme to handle instead of a continuous error. So that's the idea. Okay.
Okay.
So, we will discuss
Uh,
another question also. Yes.
yeah. So, like in the assignment, there is one particular question which is actually speaking about the de-interleaving.
Mm.
So, can you just throw some light on that?
Okay. So if the thing is, if I directly, discuss the assignment questions, then since they are meant to be graded, it won't be fair. I mean,
Yeah, that I understand.
yeah.
But the thing is, okay, so you have here 3x4 interleaver. So
Mm.
when I say from here the data out, if
Mm.
again I write it maybe kind of matrix or something, it will be 4
Yes.
cross 3, right? But again here, okay, certain bits were corrupted and so and so. So what
Mm.
exactly is going to happen at the other end?
It's just the reverse operation. So whatever was originally transmitted, you will get back the ultimately in the communication, you will get whatever transmitted. The goal is to receive exactly the same thing. So as you said correctly, the structure of the matrix will be different, the dimension will be different, and you just perform the reverse operation. That's it. And I think in week 5, details of de-interleaver was not discussed. I mean, it's just the mainly the interleaver was discussed, and it was only mentioned that the de-interleaver is doing the reverse operations.
Yep,
So
yep.
yeah, so I don't think, I mean, I should discuss, I should go into the details of any de-interleaver concepts because it's not covered. So yeah, for assignments purpose, I don't think it's required in detail. I mean, just the basic idea is enough. Just it's performing the reverse operation. So what kind of a structure do I need? That's I think is enough. Or else you can refer to any textbooks. There are many textbooks available. You can just go through them and get some idea to know more. Yeah. Okay. So question 9. Question 9 we did it, right? Yeah, question 9 we did it. Now, okay, now we are in the question number 10. Yes. So read the question number 10, everyone. So basically, interleaving is performed at the transmitter side before you do your, this error correction. So so that your forward error correction works correctly, this interleaver is used to randomize the errors to tackle the burst errors. Once the error correction is done through the channel and all, at the receiver side, you do the reverse operations, which is de-interleaving, decoupling, and then you get back your actual transmitted bits if there is no error. So it's the same. I mean, you have an M by N interleaver. So obviously you already answered the question. What will be the dimension of the interleaver? I won't say that. Of course, I mean operations will be just reverse. So the things which were row wise now becomes column wise and vice versa. So you will clearly know the dimensions. So yeah. Okay. Okay, so the 10th question says that, okay, for a forward error correction decoder, FEC decoder, which is denoted by a NK decoder. So these are standard notations. So K is actually the number of your message bits, and N is the number of the bits in the code words. So the length of the code words. So N is typically greater than K. So what happens in error control coding is that if you have some idea, you already know it, but yeah. So you take K message bits, let's say binary bits, and you encode it into N code bits, and N is greater than K typically. So you basically add extra bits to your K message bits, and that extra bits are known as your redundant bits or your parity bits that are used to protect your message bits as you transmit through the channel. So this redundancy helps in error to tackle error correction to prevent many bits from getting corrupted. That's why you need the redundancy. And they are parity bits because you essentially perform some parity, perform some XOR of a subset of the message bits. Anyways, I won't go into the details of those ECC concepts, error control coding concepts. But the idea is, okay, in this question you have a NK FEC decoder that takes in N code bits, okay, at a time. Out of those N code bits in your code word, T errors are correctable. If there are errors in T bits out of the N bits, they are correctable. So this is a T error correcting code. Okay, fine. Now an M bit burst error occurs. So M bit burst error means a chain of M bits in errors consecutive. Let's say C1, C2, so on up to Cm, they are consecutively in error. Burst error occurs when the channel occasionally goes into a fading below acceptable level, obviously, thus corrupting your M consecutive bits. That means the M bit burst error. Now consider a one error correcting 3,1 FEC decoder. So one error correcting means T is 1 here, and the parameters are N equals to 3 and K equals to 1 for this decoder because it's 3,1 decoder. So it means that okay, out of N bits I can correct T errors. So in this case it will be out of 3 bits I can correct 1 error because T is 1, N is 3, correct? Now let's say if 12 bits are transmitted into the channel and received at the receiver, what is the maximum length of burst error that can be definitely corrected at the receiver if there is no interleaver? Okay, I mean it's a at the end it's mentioned there is no interleaver. Okay, so we don't have any tool with us. So all we have is the code only. We don't have any interleaver. In this question, the case is no interleaver is present. So only the code is there. So what is the error correction capability of this code? We are mentioned that it's a one error correcting code. So at most it can correct 1 bit error. So what will be the maximum length of burst error that it can correct? Definitely, it's simply 1, right? Even if there are errors in adjacent 2 bits, it won't be able to correct, because the capability of this 3-1 code is single error correcting, right? So it can at most correct one bit error. So we don't have interleaver. That's why using interleaver, we will see the next question if we can change it or not. So the answer would be 1 simply, because we don't have any interleaver. We just have the code, and the code can correct only at most 1 error. So answer will be 1 in this case. So this was the case where we don't have interleaver, and the 3-1 code was given. Sorry, can correct up to a maximum of 1 error. So that t equals to 1. T is the number of errors that it can correct. So of course, I mean, if there are 2 errors in the sequence, it won't be able to correct. So 2 adjacent errors, or 2, I should say, consecutive errors. 2 consecutive errors, or any 2 errors as a matter of fact, it won't be able to correct. Cannot correct. So therefore, your maximum allowable length of burst error would be 1, simply based on the error correcting capability of the code itself. There is no interleaver. Fine. So this was like n was 3, k was 1, t equals to 1. Okay, it can correct only 1 error. So that's the maximum length which is allowed. Now going to our last question. So this was option A. So option A, it's only 1. Okay, now going to our last question, which is, I mean, continuation of the question number 10. If we introduce a 3x4 interleaver, what happens? The 3x4 interleaver is deployed at the transmitter, and of course corresponding dimension, I won't say the dimension, you already know it, but still I won't say it. Corresponding de-interleaver of some suitable dimension is also employed at the receiver. Then what will be the maximum length of burst error that can be surely corrected at the receiver? Now, does it remain 1? Does it change? That's the question. Okay. So I'll write 3x4 interleaver at transmitter, and of course it's also coupled with some suitable size de-interleaver at receiver end. Okay, so you see, you have 3-1 code with t equals to 1. So this is your n, this is your k. So out of n code bits, which is n is 3, the code can correct t equals to 1 error. Okay, so So the definition, you see, I use the definition of a T error correcting code. Out of the n code bits at a time, T bit errors can be corrected. So if n is 3 and T is 1, I can say this, correct? Where is the, okay, yeah, correct. So for if I construct my interleaver, so okay, for a 3x4 interleaver, how many bits will be there? Of course 12 bits, right? 3 times 4, 12 bits. Let me label them as A1, A2, A3, B1, B2, B3, C1, C2, C3, D1, D2, D3. 12 symbols are there, 12 bits are there. Okay. Okay. Now, if I construct my interleaver, how would it look like? Three by four. This is data in. This is data out. Okay. So again, data in is column wise. A1, A2, A3, then B1, B2, B3, C1, C2, C3, and finally T1, T2, T3. These are all my 12 code bits. Now, let's okay, then the question is, how many burst error can I, what's the length of the maximum length of the burst error or the consecutive errors that I can tolerate, that I can correct? Okay, so how, for that, what will be the sequence of the transmitted bits? So the transmitted data out sequence would be what? This is row wise. So A1, B1, C1, D1, first row. A2, B2, C2, D2, second row. A3, B3, C3, D3. That's the third row. Okay. Okay. Now, so in this sequence they are transmitted, and once then I do my de-interleaving. Okay, at receiver, and I once again, this is my original sequence, this is the original initial sequence, right, of 12 bits, A1, A2, A3, like this. After doing interleaving, I have a different modified sequence, A1, B1, C1. After doing de-interleaving, I once again get back my original sequence. So after de-interleaving at receiver, I have the sequence again, the same one, A1, A2, A3, B1, B2, B3, C1, C2, C3, the original one, right? Which I started with. So C1, C2, C3, and of course D1, D2, D3, 12 symbols, correct? So that's what means. I mean, you do a interleaving operation and you do just a reverse operation, de-interleaving, so your overall sequence will remain the same. So someone was asking like, what's the basic intuition? So that's the idea. Okay, so now what I can tolerate is, out of 3 bits, if one is in error, then I can correct it. Okay, so let me say where is another ink? Let me say that this A2 and let's say B2, similarly C2, they are and this similarly this B2, they are getting corrupted. Let's say so A2 B2 C2 D2 corrupted. So this is received symbol sequence. Okay, let's say you see these get corrupted. So what does it mean? So between A2 and B2, how many symbols are there? A3 B1 B2. So after every 3 bits you see one error, and that is fine with me, right? For the 3-1 code, for the 3 bits the code can correct one error. Okay, so my observation is that any this is C, this was down. So any 3 consecutive bits or symbols have how many? Only one corrupted bits or symbols. Correct? Any 3 consecutive, let's say A2 A3 B1, this 3-bit string will have only one error in A2. Similarly, you consider B1 B2 B3, there is only one error at B2. So any string of 3 bits or 3 symbols will have only one corrupted bit or symbol, and that is easily correctable. And this is correctable using my 3,1 FEC decoder. Correct, based on the definition. And so if this is our case, we assume that A2 B2 C2 D2, they are getting corrupted. So in my interleaver structure, what are my compromised bits or symbols? This entire row, A2 B2, this, okay, this is entire row, this second row, this entire second row in error. So burst error length is how much? 4 consecutive errors, right? So overall this code can tolerate a maximum burst error length of 4 once this interleaver and de-interleaver is used 3/4. Okay, that is the idea. Previously it only corrected only just one error based on its own capability of error correction. There was no interleaver or de-interleaver. But here we assume that okay, if an entire row is corrupted, if there is a burst error length of 4, then what happens in my receive symbol sequence after performing the interleaving, I see that in consecutive 3 symbols there is only one error, which is correctable using my 3,1 code. So therefore this works. So therefore maximum length of burst error that can be surely corrected, I mean guaranteed, sorry, surely corrected is 4. So it increased the error correction capability. You see, that's the application, one of the application in error control coding, application of interleaver. So option D. So option,
Sir,
yes.
sir, how you are saying that this is correctable using 3-1 FEC decoder?
So you see the
How it
definition.
can,
You see
how,
the definition. So the general definition is, for a NK decoder, out of n code bits, it can correct t bit errors. So you just take the case of 3-1 code,
okay, it
and
can correct the bit error.
so t is the number of bits that can be corrected. So for my 3-1 decoder, it is correcting one error correcting 3,1 FEC decoder. It is mentioned. That's the example that we are taking. N equals to 3, t equals to 1. So out of 3 code bits, 1 bit error can be corrected. Okay, for the 3-1 code. That's why I wrote.
Okay, so if it is said 3-1, that means one bit can be corrected out of 3.
No, I mean, these are different notation. 3-1 is the notation for n and k. These are different parameters. See, 3-1 within parenthesis, whatever is written, these are n and k, n
Yeah,
comma k.
N and K.
So n is the number of code bits, the length of the code word, okay, and k is the number of message bits. So you need not worry about the message bits now. And this t is the number of errors that can be corrected, and which is, for this 3-1 code, is one error correcting. Okay, that's actually,
No, sir, not
that's
getting.
huh. So this is
Sir,
this.
please repeat it. I am not getting.
Okay, wait. So nk code with t error correctability. Okay, 3-1 code with one error correctability. So here, what are the parameters? So this is n equals to 3, k equals to 1. I'm just comparing these two. Okay, and this is t equals to 1. So you don't mix up these two. T and k are not same. Don't mix up these two.
Yeah.
Okay, t is actually, so if you have studied some more of information theory or error control coding, t is actually related to something called your Hamming distance or minimum distance of a code. Usually we also specify another parameter called nkd, where your d is the minimum distance of code. So it's basically the minimum distance between any two code words in the code. So I'm not going into the details. So t has a connection with that d, that minimum distance, as like this. So it's like the floor of d minus 1 by 2. At most these many errors it can correct. So don't confuse t with k. Okay, so these parameters are different. So k is your number of message bits, or your message length basically, and n is the number of code bits. Okay, now the length of code word, they call it code word, and t is number of errors that the code can correct. Okay, so what happens is
Hmm.
that if you start with a, let's say, 3-bit message vector, let's say they can be binary, say 0000011, whatever. So there, this is k is 3. I'm just giving an example, sample case. Okay, or let's say, I mean, for simplicity, let's say, okay, for simplicity, let's say only 1 bit only. let's say M1. Okay. So M1 is transmitted. So M1 either it's 0 or 1, like any bit is transmitted. So this K is 1, length of the message is 1, and this is my encoder, FEC encoder. Okay, that gives me, let's say, some message vector which can be which is of size, let's say 3 for a 3,1 encoder. So it will be some M1 dash, M2 dash, M3 dash, some sequence of 3 bits. Initially you had only 1 bit, it goes to 3 bits. So that's the idea, and you add this redundancy. Actually redundancy is added, extra bits are added to for actually error correction, so that if I have some extra bits, I want to protect my original message bit, which is M1. So for that, extra bits are added. Okay, so yeah, so let's say from 0 you can encode it to 0 0 0. This is also known as the 3-bit. So this is K equals to 1, this is N equals to 3. Okay, this is called 3-bit repetition code. Okay, encoding theory. So similarly, if you have, because bits are repeated, right? So if you have 1, then 1 goes to 1 1 1. So the idea is that and then if you transmit this, if you transmit 0 0 0, okay, basically you are transmitting 0 0 is transmitted, but you first encode it to 3 zeros. Now it transmitted to the channel at the receiver. So this is transmitter at the receiver. Let's say one of the bits is corrupted. Let's say it becomes 0 0 1. Let's say the third bit is flipped. So third bit flipped, but you'll observe that, okay, out of the 3 bits I have 2 zeros, but the third bit is different, it is 1. So there has been some error. You would be able to identify there has been an error, and you will perform some majority decoding rule. So you will see that the majority of the bits are 0. So you'll assume that, okay, the corrupted bit is actually 1, so there has been a transition from 0 to 1, and you will be able to decode majority decoder to 0, that 0 was transmitted. Okay, you will understand that, okay, only one of the bits is compromised, so actually the actual message transmitted was actually 0 0 0. The third bit got flipped, and 0 0 0 means 0. So that's, I mean, that's the picture actually. So yeah, so don't get confused. Okay, N comma K code with T
So
error
it will
correction.
get automatically corrected, means majority bits.
Yeah, I mean, you can
Sir, so in
decide.
this, it will get automatically corrected since majority bits are 0 0.
Yeah, exactly. And so the, what is the conclusion? One bit can be corrected. One bit error can be corrected.
Huh.
Okay, but if it happens that, okay, it becomes, from 0 0 0 it becomes, let's say, second bit and third bit gets flipped, then it becomes 0 1 1, right? If my second and third bits
Hmm.
are flipped, then it, from 0 0 0 it becomes 0 1 1, correct?
Yes.
And then,
Yes, sir.
based on the same majority logic, I will say that, okay, I received 0 1 1, so my, I mean, out of the 3 bits, 2 bits are 1, that's the majority. So I will think that my first bit is actually corrupted. I will think that, based on the majority logic, I will think that, okay, it's actually the first bit which is
Uh,
received incorrectly.
yes.
So that will be an error case, right? So I will actually assume that originally 111 was transmitted. I will think like that, and 111 is
Mm-hmm.
what? Z1, the mapping. See this one. So, but originally 0 is transmitted. So this is wrong. So it won't work. So t equals to 2 errors will not be correctable. Okay. So here my logic will fail. So that's why if there is only one error in this scenario, okay, I'm good. I'm fine. Okay.
Yeah.
So you get the idea, right?
Hmm.
So if you
Yeah,
transmit
this is okay,
0.
sir.
Mm-hmm. So that is the thing. So that is the thing. So this is a 3,1 repetition code. Fairly example of the scenario that we discussed actually. So it can actually handle one error correcting capability is there. If
Uh-huh.
there are two errors, it fails. That's what we saw just now, right? So that is the thing.
Uh, okay.
Yeah, I mean for this question, for our question, we don't need to go into the details of error correction and all. We just need the
Hmm.
concept of interleaver and all, which I already discussed. So based on the definition is already given that out of n bits, if n consecutive bits, if I can correct t bits, that's fine. If t bits are in error, I can correct. Okay, that's fine.
Okay, okay. So with this logic, we can say that if it is a 3-1 forward error correction decoder, then
Mm.
it can correct one bit out of three.
Yeah,
Okay.
one error. It can correct one error out of three. Out of
Yeah,
any
yeah, it
three
can correct
adjacent
one
symbols.
error out of three bits.
Out of any three adjacent bits. That's the thing. Okay, that's
And
exactly what we
out of
saw
three
here.
adjacent bits.
So this this
Okay, okay,
this
okay, sir.
picture you
Yeah, yeah,
see,
yeah.
A2 and B2, C2, D2 are compromised. So you take any three adjacent bits, you will find only one bit in error, which is correctable,
Yeah,
right?
yeah, yeah, yeah.
Yeah, that is the
Yeah,
idea. That is the idea.
yeah.
Okay.
So this is one possibility you have taken, na?
I mean, that's the best you can. That's the best you can. It is asked in the question
Yeah,
that
A2, B2, C2, D2.
what is the maximum length of burst error that can be
Yeah,
shown?
maximum, and maximum can be four only.
Facts 4 only. Yes, that's the best you can do.
Yeah,
Okay.
yeah, yeah, yeah. Okay, okay, sir. Thank you.
Yes, yes, yes,
Yeah.
yes. Good. So we have come to the end of today's discussions. So I'm not sure if I took pretty long than required for all the questions, but I just wanted to, ensure that all of us on the same page. So, but overall, some questions are straight away, formula based, so you can solve it in very less time. So hopefully this gave you some idea on how to approach the assignment problems, and like someone was asking, so your final exam will have the same pattern as similar pattern as that of the assignments. So yeah, and feel free to drop your queries in the discussion forum. You can email me also. So yeah, and yeah, get your doubts cleared, and just focus on the lectures. Whatever the concepts are discussed in the lectures, they are, I think, sufficient. So yeah, yeah, we digressed our discussion. We moved to covered certain lot of other things of error correction, which was not really required for our problem, but just for understanding we discussed. But yeah, yeah. So I think I'm done with today's session. If there's any queries or any comments, people can, okay, post your email ID. Okay, I have given it before also, so anyways I'll just write it. Yeah, that's my email ID. You can drop me any email anytime. I'll try to reply. So yeah.
Sir, please show it.
Sorry.
It is not visible.
Oh,
Can you yeah, EE21D002.
at ismail.iitm.ac.in. I have posted in the chat box. You can open the chat box and it should be visible.
Yeah, 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 yeah.
Hmm. Okay, so thank you for your time. If there are no queries and nothing, then we can stop the recording for today, and we can meet again on next Tuesday. All right, so I'll stop the recording. Thanks.